Okay. All right. So graphs of logarithms. So remember that a logarithm has an output. I see that it's frozen. Logarithm has an output of. Did I leave the clicky over there by you, Zach? We press the freeze button. It's like bottom rightish, kind of. Thank you, sir. So logarithms are used in the real world, really in chemistry. But the most important thing is to remember that logarithms are the what? Why were logs invented? Why do we have those? Because of what? There's no other way for us to find the inverse of an exponential function, right? So we came up with this thing called log. So we're going to look at this first function. I need to plug in. We're going to look at this first function, y equals log base 3 of x, and its inverse, y equals 3 to the power of x. Know that the inverse is the exponential function. The inverse is the exponential function. So let's go ahead and fill out our table of values. Let's go ahead and fill out our table of values. Okay. So if x is negative 2, we're just filling out our table right here using this function y equals 3 to the power of x. If x is negative 2, 3 to the negative 2 power is the same thing as 1 over 3 squared, which is 1/9. 3 to the negative 1 power is the same thing as 1 over 3 to the first power, which is just 1/3. 3 to the 0 power, well, any non-zero number, so like any number other than 0 to the 0 power is 1. 3 to the first is 3, and 3 squared is 9. Let's go ahead and graph these ordered pairs. So when x is negative 2, y is 1/9. I'm just putting that as close to the x-axis as I can. When x is negative 1, y is 1/3, as close, like a little bit higher. I don't know if you can see my dot or not on the board. When x is 0, y is 1. When x is 1, y is 3. And when x is 2, y is 9. So this is the exponential function y equals 3 to the power of x. If I didn't know how to find those, I could just go to y equals and do what? In my calculator, y equals and put in the equation and ask for a table. Yeah, okay. So the function y equals log base 3 of x is the inverse. These are inverses. So what do we know about the ordered pairs? They just flip them. So my input is going to be 1/9, gives me an output of negative 2. My input of 1/3 gives me an output of negative 1. My input of 1 gives me an output of 0. My input of 3 gives me an output of 1. My input of 9 gives me an output of 2. So let's see. When x is 1/9, and that's really, really, really close to the y-axis, I drop down to negative 2. So I'm just smidging it right there. When x is 1/3, I am at negative 1. When x is 1, y is 0. When x is 3, y is 1. And when x is 9, y is 2. So this is the function y equals log base 3 of x. Remember that they're inverses. What do we know about inverses? What are they symmetrical about? Do you guys remember? These two lines are symmetrical about the line y equals x. So this is the line y equals x. Are we good? Are we awake? I'll keep that there for a second. I see some of you guys are still graphing. So step B says graph y equals 3 of x. We already did and label it. Got it. Graph y equals log base 3 of x. We already did and we labeled it. Question C says, hey, what is the domain and the range for both of those functions? So let's look at the red function. That's the exponential function y equals 3 of x. What is the domain for that? What are my input values able to be? What numbers can I let x be? Well, we see right here that x is a negative number, right? We also see that it can be 0 and it's positive. So what do we say when, what's a typical domain? All real numbers. Yeah, x is all real numbers. Our domain is all real numbers. Let's talk about the range. Remember that the range is the y values. So when you look at y equals 3 to the power of x, that exponential function, what do we notice? Are the y values ever negative? Are the y values ever negative on y equals 3 of x? No, they're not. They get really, 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 really small, but they never go negative. So that means that y, all of our output values are greater than 0. Now let's look at the inverse of the function. Let's look at the inverse, which is y equals log base 3 of x. Tell me about that domain. Look at all of our input values on the inverse function, right down here in this like light blue. Did we use any negatives? No. So what do you think is going to be the domain? X is greater than 0. X is greater than 0. Well, let's talk about our range. What's the smallest y value? What's the smallest our y's go? Negative infinity. That really goes on forever. Do you see the arrow that I'm kind of dragging down here? What's the largest it goes to? All real numbers. Yes, good job. All real numbers. Okay. Questions? Okay, using your calculator, we're going to sketch the graph of y equals log base 10 of x. And then we're going to label our graph. So I'm going to freeze the screen and just pull up. You're going to freeze it for us, Zach. I'm going to go to Desmos. Thank you. All right, everybody grab their calculator. Remember that log base 10 is called what on your calculator? You can do it one of two ways. It has a special name. Do you remember? It's just the log button. Yeah, it's just the log button, okay? You could just use the log button. So I'm just going to go and graph it in Desmos so you guys can see it, but you guys are going to graph it on your calculator. So if you use the log button, you're just going to do log y equals log button x, right? Y equals log button x. If you use the math button and you arrow all the way down to the capital A where it's log base, you're going to put in the 10 there, okay? Zach, will you unfreeze it, please and thank you? Okay, so when I look at my graph, I specifically want to know what happens when x is 10, right? Because that's the length or that like the x values of my graph. So I look at the numbers -2 in my table and -1. I know that is centered weird. I'm going to try and pull that a little bit so you guys can see it. I'm trying to make it so you guys can see the numbers on the table of values. And I know that you can't, but it's undefined at -2, it's undefined at -1, it's undefined at 0. But when x is 1, my output is 0. And then I used 2. I graphed it, what happened at 2. I also graphed what happened when x is 5. And then I did when x is 10. So you're just going to sketch a graph. You are just going to sketch a graph. So in my graph over here, I'm using the ordered pairs. Well, I know that when x is 10, my output is 1. I know that when x is 1, my output is 0. And 5 was like a 0.6. So I'm just sketching my graph, just something like that. You're just making a sketch. So what do we know about our domain? Same as before, x has to be greater than 0. What do we know about our range? All real numbers. Are you with me? Guys, pick your head up off your desk. Michael, pick your head up, please, and thank you. You can make a table of values if that'll help you. We did 1 is 0. I did 2. What does it say on your output in your table? Wasn't 2 like a 0.3 something? And then I did 5, which was 0.69. And when x is 10, my output is 1. You can just graph those points if that'll make it easier for you. You just put the function into your table or your y equals and get a table. Raise your hand if you need me to wait. So I have the ordered pair 1, 0, 2, negative 3, 5 point, sorry, not 2, negative 3, 2.3, 5.69, and 10, 1. Those are abouts. Those are like rounding, Reese, okay? Alrighty. Question number 3. It says, which of the following equations describes the graph below? Well, hopefully we know that, remember, log functions can never be negative. So I'm just sketching a log function right here. Do you guys see that in green? I'm just sketching a log function. So if I think about transformations, you with us, Kane? If I think about when I learned how to transform functions, if this is the parent function, right? Y equals log base 2 of x, or y equals log base 3 of x. How much does it move? Is it moving to the right or to the left? Looking at the parent function, which is green, how do I move? How does that black graph move? This is the parent function. You are comparing it to this. How much does it move? Does it move to the right or to the left? Yellow to pink, compare those. Is the yellow function moving to the right to become the pink, or is it moving to the left? It's moving to the left. Let's count how many units it moves. From here to here, how many units does it move? Yeah. So if something goes left 3, that looks like an x plus 3 inside the function, right? That's just from chapter 1, parent functions, transformations of functions, okay? So this is out and this is out. So I know that it's got to be down to question 3 or 4, like sample 3 or 4. So after you figure out the shift, choose a point. Let's try the ordered pair 1, 1, and you're just going to plug it in. So if y equals log base 2 of x plus 3 minus 1, if I use the ordered pair 1, 1, that means I'm replacing x and y with a 1. Tell me if this is true. Is 1 equal to the log base 2 of 1 plus 3 minus 1? I don't know where my minus 1 went here. So let's see. What is log base 2 of 4? 2 to what power equals 4? 2. So this is the same thing as saying 1 equals 2 minus 1. Is that true or false? It's true. So the function that this has to be is the log base 2 function. I'm going to check the log base 3 just to make sure we understand. So log base 3 of x plus 3 minus 1. So again, I'm going to let x and y both equal 1. I'm just going to check it. I'm picking a point, and I'm checking to see if it works. So 1 equals the log base 3 of, let's see, 1 plus 3 minus 1. So this log base 3, 3 to what power equals 4? Well, nothing nice, right? Nothing nice, so it's definitely not that. Okay, so it's answer choice 3. So first you have to figure out the shift. We saw that it went to the left 3, went left 3, which is represented by the x plus 3. And then we just figured out, we plugged in those 2 points. Check to see which one makes a true statement. All right, question number 4 says, determine the domain of this function. You should have that filled out, right?
Yeah, we should.
Okay. Determine the domain of this function. So let's talk about this for a second. What do we know about the domain of log functions? We've written twice about the domain of a log function. Go to the front page. What do we know about the domain of a log function? X has to be greater than 0. So for our domain, X is greater than 0. Okay, well, that means, like typically we write it as log of some base of X. That just means that this is representing the function that we're evaluating, right? The input. So it means that 3x minus 4 must be positive or greater than 0. So we can do that and write what to solve for our, what can we do if we know that this has to be greater than 0? Well, let's just write an inequality. This has to be greater than 0. And let's actually figure out what x has to be greater than. Okay? Well, let's solve it. I'm going to add 4 to both sides. So 3x is greater than 4, and I'm dividing by 3. So x actually has to be greater than 4/3, which is a little bit bigger than 1. X has to be greater than 4/3. It says state your answer, state your domain, and set builder notation. I'm going to write that right here. The domain means all of my x values such that x is greater than 4/3. So remember that log functions, the domain is positive. It's got to be greater than 0, means it's positive. So if you have to evaluate and find the domain, you just set whatever your x substitution, I guess, is inside of that function, whatever you're evaluating your function at, set that greater than 0 and simplify. Okay, you're just going to write an inequality. All right, I'm going to move up. So logarithms with bases larger than 1 are always increasing. This increasing nature can be seen by calculating the average rate of change. So consider the common log, log base 10, and we're going to figure out the average rate of change, which is what? Average rate of change is a fancy way of saying what? Slope. This is the same thing as asking for the slope of f of x, which is the natural log function, or not the natural log, the common log function of the interval 1 to 10. So I'm just going to first of all remind myself that slope is my change in y over my change in x. So my y is really log of what? 10 minus log of 1. That's that's the interval that I'm allowing x to be over my change in x, which is 10 minus 1. So remember that this is a natural log, or not a natural log. I got to stop saying that. This is a common log. So this is no different than saying 10, because remember, we don't write it as base 10, but it's really there. 10 to what power equals 10? 10 to the first power. So log 10 is the same thing as 1. 10 to what power equals 1? 0. So my output is 0. And what is 10 minus 1? It's 9. So the average rate of change of the common log function between the interval 1 and 10 is 1/9. Up 1 over 9. Okay. Let's do that same thing. We're going to calculate the average rate of change using the interval of 1 to 100. So the log base 10 of 100 minus the log base 10 of 1 over 100 minus 1. So 10 to what power is 100? 10 to what power is 1? So 2 minus 0 on the top. 100 minus 1 is 99. So this has an average rate of change of 2 over 99. Is the rate of change increasing like drastically? Is it growing really rapid? Is it going to have a nice slant, or is it kind of leveling off? What do you think? What's happening to the slope? Is 1/9 bigger or smaller than 2 over 99? It's bigger. 1/9 is much bigger. 1/9 is the decimal 0.11. What is 2 divided by 99 as a decimal? Okay. So we know that as we increase the x value, the slope gets less, right? So let's write that. The slope is getting smaller as x gets bigger. That's really what's happening. Our slope is getting smaller as x gets bigger. Hopefully, we can see this in the graph. Writing that we can see this in the graph above. Okay. Hopefully, we can see this in the graph